Okay, so let me share the screen. Oh, I think it was. I think stop. Okay, let me share the screen. What was that? Yes. Good. So yeah, I'm sharing the screen. I think you should be able to watch it now. Do you see the screen?
Yes.
Great. Okay. So today we are continuing our graph algorithms, and we talk about the shortest path. Actually, we already talked about a few problems before that I want to remind you that is relevant. We talk about the DAGs, directed acyclic graphs, and we mentioned about the topological sort there. So topological sort was that if you have a DAG, you want to find an ordering of the vertices such that all of them are from left to right. So 1, 2, 3, 4. And so there is no edge like this in the graph. No such edge in the graph. And this 1, 2, 3, 4, it might be different from the like the idea of the vertices that are given to you. You want to find this order such as this happens. And we discussed that the running time of this algorithm would be indeed order V plus E. V the number of vertices, E the number of edges. So we talk about that. We talk also about all pair shortest paths. So all pair shortest path, and that was, we call it APSP. And for that, we talk about Floyd-Warshall. Floyd-Warshall, which was a very simple algorithm with 3 loops inside, but the order of the loops were important. And it was n to the order n to the 3. I mentioned that getting anything better than n to the 3, like 3 minus epsilon for epsilon greater than 0, that's a very important open problem. And actually, this one works for even for negative weights. So you can have negative weights. As long as there is no negative cycle. Good. And that was the idea of K-paths that we discussed. It was induction. There was 3 loops, and the induction was on the, essentially, like we had it M, X, and Y, and the induction was on the first, the parameter of the first loop, M. So we have n to the 3, and this one found all pair shortest path. Between any 2 pairs of vertices, we could find the shortest path. So, and that works with the negative base. But the running time was ordered n to the 3. Today we want to talk about another famous algorithm here, the Dijkstra algorithm. So the Dijkstra algorithm is the one. This is the one for single source shortest path. Source shortest path. And again, as I mentioned, single source shortest path is the case that you want to find the shortest path from one vertex to everyone else. That is from the single source, and this is the source. I mentioned that a single sink is the same problem because you can just reverse all the. So if you want to do that, you can just reverse all the direction of all edges, and then single source and single sink would be the same algorithm. So this is the Dijkstra algorithm for single source shortest path, and this one works only for positive weights. We talk about another algorithm, Bellman Ford, after this one. Maybe next session. Bellman Ford. That is also a single source shortest path that works also for negative weights. So that gives you a good ideas about the things that we have and we want to discuss. So we talk about the single source case, but and all of these are about the directed graph. So everything here we talk about is the directed graph. So what is, let me mention the problem more precisely that you are given a directed graph G with weight or length associated with edges. So again, we are considering, we call weighted graph, but the weight can be the cost, it can be the length, it can be the time or anything. But in general, we call them weighted graph. You want to find a shortest path from V to all other vertices of G. That's the thing that I mentioned. It is called single source. Yeah, and we talk about the shortest path. We could say lightest path or the minimum time path, but that's the one that we are considering. And as the one that we mentioned before, the length of a path is the sum of the lengths of its edges. Good. Now, let's talk about DAGs before. Other things, let me clean everything. Any questions so far? Great. So, let's start with DAGs. So, for DAGs, as we discussed, you can find a topological sort of the vertices such that all of these edges in the graph are from left to right. So this is, I want to call it K, and this is F. Okay, so for a DAGs, we have these two properties. Like, what is the first one? So if Z, so consider Z. So this is the vertex Z, whose label is K. Like in the topological order, as I mentioned, we are giving the numbers from 1 to n to vertices such that this property is satisfied. So if you consider a vertex Z, we know that there is no back edges. So let me just mention this one. We know that there is no back edges. So as a result, we know that there is no path from Z to any vertices before Z. So there is no vertices, there is no path or no edges from this vertex Z that has label K to vertices who have label 1 to K minus 1 or less than K. Also, similarly, there is no path from or no edges, actually. When there is no edges, of course, there is no path. From the vertices which, whose index or their topological sort number is greater than k to vertex z. So everything is just forward. There is nothing backward. Good. So assume that good. Yeah. So assume that this vertex 1, it's again, its order in topological sort is 1, but assume this vertex 1 is actually the vertex V. Now, what is the induction hypothesis that we have? So this is the induction hypothesis. We want to say so this is the induction hypothesis. We want to say, given a topological ordering, we know how to find the length of the shortest path from V to the first n-1 vertices. Good. So this is the topological order. So I want to say that we can find the shortest path from V, the first vertex. So V is the vertex that delays the source, essentially. We are assuming the V is the source that we want to find the shortest path from V to everyone else. If there are some vertices before V, you can always delete them because there is no edges, no paths from V to them, as we discussed. So V is the first vertex. That's the reason that we are assuming the V is the first vertex. We want to find the shortest path from V to n vertices here. And assume that actually here we know the shortest path from V to n-. Good. Now let's consider the vertex. Yes, W. Actually, let's consider the vertex Z. So this is the same vertex. So let's just. So this is a vertex Z that we have. So we want to find, so we know the shortest path from V to n-1, and assume that this is somehow, we have stored them in a matrix SP. So SP of a vertex, say W, it means the shortest path. So this is the shortest path. From V to W. Good. So we know that. And here from essentially for the first n-1 vertices, we have it. Now we want to find SP of Z. Good. So, and this is the induction hypothesis that we have discussed. Let me just erase this one and then draw it again. Okay, so what do we do? For Z, we know that there is all the edges that goes are essentially from Z, you can only go forward. There is nothing backward from Z. So there is no backwards. What's the meaning of that? It means that first, by induction hypothesis, we are assuming that we know the shortest path from V to all of these n-1 vertices. Now we want to find the shortest path to Z. And Z is the nth vertex in the topological sort of this directed acyclic graph. So we are talking about DAGs here, directed acyclic graphs. Okay. Now, for this vertex Z, there is no such edge like the backward edges. So what's the meaning of that? So it means that all the edges here should be just forward edges. So we know that the shortest path from V to Z, it should come from some vertex before, because there is no, so there was no backward edges. So the shortest path from V to Z, it should come in one of these vertices, like consider the last vertex from the shortest path from V to Z, and we call it W. We know that the W should, of course, appear after V, and it should be one of these vertices before Z. So it should be essentially one of these vertices that we are using this property. So that is a star property. So there should be a vertex W if there is a shortest path from V to Z. By the way, it might be the case that there is no path from V to Z. So in that case, it would be just infinity. And that is totally fine. So for example, here, if you consider vertex 1 and 2, there is no path from 1 to 2. In that case, the SP of 2 would be just infinity. Otherwise, then it should be a one vertex. So we are initializing this array SP, the shortest path, equal to infinity, except V, which is 0. So the basis of induction is the case of n is equal to 1. What is the SP of V? SP of V would be equal to 0. And SP of everything else would be infinity. Now, this is the vertex W, which is before Z and after V. And then we know that from here, from V to here, we took some path. But the path from V to W, that should be shortest path. That's very important. If it is not a shortest path, then you can replace it with a shorter path, and you find a shorter path for W. So, and in general for Z, because this green one was a shortest path. There might be several shortest paths as well, but consider a shortest path from V to Z. It should have a vertex W labeled from 1 to n. And the path, the subpath from V to W, that should be a shortest path. So what's the meaning of that? The meaning of that is this one. SP of Z is equal to min of over all W's, where index of W, by index I mean the shortest topological sort index. So the index of W is less than or equal to n in this case, actually less than n in this case. Then this is the minimum. What would be the minimum? Would be SP of W plus what? Plus the weight or length of, I will say length, say just weight of W to Z. So you need to take over all vertices W that their index is between essentially 1 to n. Over all vertices W, find the one that has the shorter path. And that would be the shortest path to Z. And that is exactly by definition, as I mentioned, this is by induction, that if there is a shortest path from V to Z, otherwise it would be SP of Z would be infinity. there should be such a vertex W. This part from V to W should be the shortest path, and then you should have an edge from W to Z. So you will sum it up, and you will take minimum over everything. So that's the whole algorithm to find the shortest path in DAGs. So let me just come down. Great. So this is actually the code. For this. Good. So what is the code? So this is the all-pair shortest path. So what do we do is very simple. So this is the algorithm that for the graph G and the V, we want to find the shortest path. So we know that the SP of V is equal to 0, as I mentioned, and SP of W for W not equal to V is equal to infinity, as I mentioned. So then what do we do for I equal to 1 to N? And what is N? We are assuming that we have done a topological sort before. So we are assuming here, before everything, a topological sort. So sort is done before. So we have done a topological sort before. And as I discussed, the running time of that topological sort would be V plus E. So then what do we do? Then for all W, such that WZ belongs to E, and again, so this 1 to N, this is the topological sort order. So this one is the topological sort order. According to that, we are doing that. So for all W, such that WZ belongs to E, if the path through vertex W is shorter than the current path for vertex Z, and again, SP of Z is infinity at the beginning. So if there is any path, then it would be less than infinity. So if there is even one path, we get less than infinity. Then you will just update Z. This is the minimum part that we talked about it here. We just take the minimum, and this is exactly the minimum part that we are taking. What is the running time of this algorithm? So the topological sort, as we discussed, that actually, so the topological sort, let me just delete a little bit, erase them a little bit. Good. Yes. So we know that the topological sort needs order V plus E that we discussed. Now here is this algorithm. We check every vertex and every edge only once. Why? Because if you see that we are just going through this order, so we are going through all vertices N, and for each of them, we only check all the edges that are coming to this vertex. Over them, we are taking the minimum. So we take the minimum over all of them. It means that every vertex and every edge will be checked at most once. Thus, the running time of these other loops that we are talking here is also order V plus E. Thus, the total running time of our algorithm, it would be V plus E. So this algorithm for DAGs, we can get order V plus E. Does it make sense? Any question? Good. Let me clear everything. Good. Now, what about for general directed graph? So this is the one that we talk about DAGs, but general directed graph, what's the main difference? As we discussed, directed acyclic graph, they don't have any cycle. So in directed acyclic graph, we don't have such cycles like this. These are the vertices of the graph. But in general graphs, actually, we have such kind of things. We may have. Good. So now we want to solve the problem for general graphs. So the running time that we got it is, v plus the size of v plus, when I say v means the size of v, plus e, or the size of e. Now, as we discussed previous time, I just repeated. If you have an undirected graph and there is an edge between u and v, you can always replace this vertex with two directed edges, like go from v here and here. And the length, if the length of this guy is c, then you will put c here and c here. So this is equivalent. So it means that if your graph is undirected and you want to find the shortest path, then you can first make it directed and then using this reduction and they can solve the problem. And this is the important one. So generally directed, here it says that the directed graphs are more general than undirected graphs. And this is generally true. So for other problems as well, if this is an undirected graph, generally you can replace it with this kind of both forward and backward edges. And it means that the general graphs are harder problems. Or we say that there is a reduction from undirected graphs to directed graphs. It means that undirected graphs can be solved with directed graphs. We see more of that for the MP hardness or MP completeness. So we don't have this good property of DAGs, this star property that there is no like kind of back edges, everything is forward edges. We don't have this one because if you have a cycle, by definition, you cannot order it such that all the edges are forward. There should be at least one backward edges. However, we cannot get exactly that, but it is something similar to that we can get it. And the running time of the algorithm here, it would be the final algorithm would be size of v plus size of e, all of them times log n. So we have a log n factor more comparing to directed acyclic graph. So, what is the assumption here? So assumption is this one. Given a graph and a vertex v, so here we cannot say we talk about the topological sort. That's the reason that we need to talk about somehow similar. We are assuming that we know the k vertices. So given a vertex in this graph G and given a vertex v, we want to say that we know there are k vertices that are closest to v. So these are the k vertices, vertices closest to v. So these are the first k vertices closest to v. And we know, and you can order them. So this is, if you want, you can order them. The first vertex, which is closest to v, then the second closest to v, and so on and so forth. This is the k vertices closest to v. We want to find, and we know that this the shortest path from v to these k vertices. And then we want to find the vertex k plus 1. So assuming that we know the k vertices which are closest to V and the length of the shortest path to them, we want to say that the induction hypothesis is correct also for k plus 1. It means that this is some kind of algorithm designed by induction that we have seen a lot, that now for the next vertex, k plus 1, also we can find such a vertex and the shortest path. Good. So that's the assumption. Now here, consider this vertex V and consider all vertices that are closest to V. So this is V, and we call them Vk. No, sorry. So this is actually, let me just do that one. So this is the Vk. And now the other, so we want to, and this is the rest of V. So this is the rest of V. So this is V minus Vk. What is the goal? The goal is that we want to find a vertex here. We call it again the vertex Z. So we want to find a vertex Z here, such that this vertex is the next, like it is the k plus 1 vertex in terms of being closest to V. Good. So we want to find the vertex. Now, assuming that this is the vertex Z that has the, this is the k plus first vertex. So consider the path from V to Z. This is the shortest path from V to Z. Good. And so far, the k, these are the Vk are the first, these are the closest k vertices. We denoted them by Vk. Now, consider this vertex V. So this part is very similar to DAG. We know that in the shortest path from V to Z, there should be one vertex before Z. So we call this vertex W. I want to claim that this vertex W actually should be in Vk. Why? What happens if it is not the case? So if there is a vertex, another vertex W here, such that the shortest path from V to Z is going to vertex W, and W actually belongs to V minus Vk. We know that the edge, so we know that the weight of W Z is greater than or equal to 0. That's the assumption that we had it, the non-negativity assumption that we have it for Dijkstra. We didn't have this, we didn't need to have this assumption for all pair shortest path Floyd-Warshall algorithm. That worked even there was a negative weights. But here, this WZ, we know that it is greater than or equal to 0. So what's the meaning of that? It means that there is another vertex W that it is closer to essentially V, because this is greater than or equal to Z. And we could just talk about W instead of Z. I mean, if it is equal to 0, so W and Z, there is no difference between them. So in that case, we can go to, if we want to be a bit more formal, we can say that find the vertex, the next vertex that we want to add it, find the vertex that has closest vertex among the rest of the vertices to V. And if there are several vertices which have the same exact shortest path, then consider the one that has the minimum number of hops, like the number of the number of vertices in the path. So good. So in that case, we are saying that if there is a vertex, if there is this vertex Z, and if the vertex just before that, if it belongs to V minus Vk, then in that case, we can consider W. This, if the vertex before Z is W, then we can consider the vertex W and make this argument because the path from V to W is at least is less than or equal to the shortest path from V to Z. So that's the main critical point. So it means that for Z, the vertex just before that, it should be in VK. So there should be no V like this, no W like this. Let me just erase it. So there is no other things. This one and this other. Good. So now we are done essentially. Why? Because here, if you consider this vertex W, so we know that there is an edge here from W to Z, and then we know that the shortest path from V to W, that should be the shortest path. That's exactly the same thing that we had it for. That exactly the same thing that we had it for DAGs. So what's the meaning of that? It means that SP of V, this is the K plus first guy, should be equal to mean of SP of W plus this is the weight of this weight is weight actually, or length of W to Z. And this should be taken, this minimum V for all vertices V belong to VK. So very similar things. In some sense, we are finding the ordering. In the DAGs, we had this topological sort, which was a natural ordering or sorting. Here, we will find another ordering. And this ordering is just according to the distance from V to those vertices, which is SP of Z. So how can we find this vertex V? That's the thing that we will do that. So we will go, and for all vertices in here, V minus VK, we will compute what is this what is SP of Z, and we will take the vertex Z that has the minimum one. That minimum guy, as we argued, that guy should be the K plus first vertex, which is closest to V. So again, we are computing for each Z this quantity, and then among all of these vertices in V minus VK, the one that has the minimum SP of V, that would be the next vertex that we will consider it, and then we will add this guy, and this becomes V of K plus 1. So we will just add this other guy to the set, and that would be the V of K plus. Does it make sense? So this is actually the way that we are doing, like again, algorithm designed by induction. Z will be added, and then you will repeat this one. So now we have VK plus 1, then you add the next vertex, and so on until you are seeing the whole vertices of the graph. In particular case, if the graph is disconnected, V cannot reach some of them, those other guys, the SP of those guys remains infinity. Again, we are initializing everything with SP of essentially all vertices would be infinity except V that would be 0. And hey, here, by the way, again, the basis of induction would be V. Essentially, V1 would include only V. And of course, in that case, we know that, so here, this is the V would be the first closest vertex to itself. because the weight from V to V would be 0. So that's essentially the induction. So now let's see the algorithm. Let me just erase some of these. Good. So let's. Yes. So this is the Dijkstra algorithm. So this is the whole Dijkstra algorithm that we are talking about. So what do we do? Exactly the same thing that we have done it for DAGs. So we are here we are not running a topological sort order as we have done it in the previous case, because I mean there is no such kind of topological sort order and we don't need it as well. So we first initialize everything. This is the basis of induction, and SP of W is equal to infinity for anything else. And here mark W essentially means Markov V. So here we have the Markov V is equal to true, and the Markov W for everything else would be false. Those vertices, so mark W is equal to true means W is belonging to this VK. So for all vertices that are in VK, and this K increases, so K becomes K plus 1, etc., we are just making sure that the mark of W is equal to true. And for everything else would be 0. So here, actually, the mark of V is also equal to. Again, this is the basis of induction. In this case, V1 has only vertex V in it. Good. What do we do for the rest? We say that while there exists an unmarked vertex, so that's exactly the thing. So unmarked vertex means there is a vertex which is not in VK. So there is one vertex outside. So there is a vertex in V minus VK. Good. Let W be an unmarked vertex such that SP of W is minimal. So among all these vertices here, V minus VK, consider the vertex that has the SP of, I mean, here is talking actually about yeah. So here we are finding the one vertex. So we are assuming that we have, by induction hypothesis, also we can assume that you know the SP of all vertices so far. Among those, this is the one that we computed. And we say that among all these vertices, consider the vertex W that has the minimum shortest path so far. And this SP of W is currently is the one that, say, assuming the shortest path that goes through like VK, what is the best estimate that we have for these vertices? So among them, the vertex that has the minimum W is the one that we will add to set VK. So this is this W, we will find it, we will add it here. Now, when we are adding this W, this is the way that we update the estimates. For all edges that are going outside of W, for these guys, now because W belongs to VK plus 1, if the edge that there exists from W to those V guys is better than the current estimate of the shortest path to Z, we will update it. So what do we do here? So we say that, so of course, mark of W would be true. It means that now W belongs to VK plus 1. For all edges WZ, that Z is an unmarked. So for all these that are remaining vertices in V minus VK, if the pass, if you consider the shortest path from W plus the length of WZ, if this is less than the current estimate for SP of Z, then update SP of Z, because now using W, we can find the better things. And now actually W can be added because W is already added to the set VK because its mark is also true. So this is the way that actually we run that. So instead of, the way that we have described before, so for each Z, you are going to all vertices V minus VK, find the vertex Z that has the minimum, and then you will add it. In some sense, we are assuming that SP of those vertices in V minus VK, we had already a good estimate. So among them, we will consider a vertex W that has the minimum estimate for shortest path. That estimate actually should be the actual shortest path that you can get it through VK. We will add this W, since this W guy is coming from outside to inside. And then for all edges that are going from W to vertices outside of VK or VK plus 1, we will update the shortest path, because now that W has been added, there might be shorter path through W, and W is the next vertex that we have added. So that's essentially the whole algorithm. So any question about the algorithm?
So for the line where like such that Z is unmarked for all WZ such that Z is unmarked, are we looking at the mark of the vertex Z itself or the edge from W to Z?
Sorry, can you repeat the question?
For the line for all edges WZ such that Z is unmarked, are we looking at the mark of Z or the edge from W to Z?
So let me see. So is this line correct? The one that I put the arrow there. You see that for all edges WZ such that Z is unmarked. So I mean, Z should be unmarked. And there should be an edge from W to Z. Good?
Oh, right.
Yeah. So there should be an edge from W to Z, and Z should be unmarked. Then we will, if the path through W is better than the current estimate that we have, we will update. Good? Great. Yeah, so that's the whole algorithm. It's very similar actually to this algorithm that we mentioned for topological sort. And this is somehow the idea when you get some problem that is for some general graph. Maybe you want to simplify, say, what can we do for DAGs? Generally for DAGs would be easier. Or sometime, I mean, according to the problem, different graphs might be easier than others. First, you are trying to solve those graphs that you can solve it, or those instances that you can solve, then you will come for a more general case. Good. Now, let's consider the time complexity of this algorithm. So let me just clear this guy and then talk about the time complexity. Good. So the time complexity of this algorithm. Good. So of course, I mean, here we have this step, that this step is order n, or n and v. So let me just do it. Order size of v. Now, we say that while there exists an unmarked vertex, do this one. Let W be an unmarked vertex such that SP is minimal. So this one, we need to see what is the running time of this step, and we will talk about it. So we need to find a vertex in V minus Vk such that SP of W is minimal or minimized. Then what do we do? This part is easy. For all edges WZ such that Z is unmarked, do this. If the edge, the shortest, the one that is goes through W is shorter than estimate for Z, then update it. So all this part, this would be order E. Because each edge, exactly we see it once. So each edge W to Z, we will see it only once. This is the time that we are seeing W, and then we are updating all estimates for Z's. So all outgoing guys, Z prime, Z double prime, etc. So each edge here will be seen only once. So far we have paid like order V for some initializations. And we have this order E for the rest of these guys. The only part is that, like here, we are finding this W that has unmarked vertex and has and SPW is minimal. So also this the number of times that we are doing this order is order V. I mean, generally V is less than order E, but there are some specific cases. This is an empty graph. There are only V vertices and no edges. In that case, of course, V is larger than E. But generally, we expect that the graph is at least a 3. Good. So now, what would be the running time of this algorithm? We have order V here. I want to talk that, I will say how you can find a vertex which is SP of W is minimal, and that will take order like N. Actually, we are using the heap or priority queue for this step. So if you remember, so what do we do here? All these SP of W, we will actually keep them in a heap, in a min heap or priority queue. These are the same things. And we talk about that, like, for example, in C++ or Python also, there are some packages that they have this one. So this is the priority queue that we just make sure SP of W is kept in such a thing. So if you remember in the heap things, deleting the minimum guy, the guy that has the minimum value was order log n, the depth of the heap. So we are using here order log n to find this guy. So the running time here, log n again, n is equal to size of V. So here, actually, the running time of this becomes order V times log V. Here also, we are doing exactly this one. But here, when we update this guy, so we say that if it is less than that, then update it. This updates here is just order 1. But we need to update the heap. So this is also a structure that we have seen it before. This is very similar to the case that we were inserting a vertex. So when we change SP of Z, SP of Z can go only down. And this is the min heap. So in a min heap, we knew that the min guy is here. So the min guy is at the top. This step, and now we are considering a vertex Z here. And we may just decrease the value of Z. Because, I mean, if this is SP of Z is greater than that, then we are just reducing the value of Z. So in that case, it means that Z may go a little bit higher in this heap. So this is the heap structure. So here, actually, Z may go a little bit higher in the heap. And that's exactly similar to insert. So this one, update one, would be order log n as well. because the size of this for each vertex, so the size of this heap would be at most the size of V. So the insert here, it is, as I mentioned, this is very similar to insert. This one essentially is the delete min. This update is essentially equivalent of insert. We are inserting. So this is the delete min, which was order log n or log size of V, and the update, which is insert, which is order log V. And the size of this heap essentially would be at most V. So then what would be the running time? The running time of this guy becomes also E times log V. So what would be the total running time of this algorithm? The total running time of this algorithm would be order E plus V times log V. So the only things that we have in extra here comparing to this algorithm for the DAGs is log V part that we have it. So this is the log V. Again, so I will just repeat this one. So let me just clear everything here. So this is the implementation. We are using the, so as we mentioned, there are two parts here. This is one part here. That we are essentially, we are doing the delete min. So what do we do? So that's essentially the thing that we are doing. So when we are creating this one, we are also creating a min heap here. Min heap means, or min priority queue means that the guy has the minimum is the top. So that's the thing that we are talking about. So the minimum is here. So then this one, so and we are inserting all of these SP values. All of them will be, so all these SP values will go inside this heap. So the size of this would be, so originally the size of this heap would be order V. Good. So the data structure that we are using here would be the heap, and then we will so we will keep all vertices not in VK in the heap. So what do we do? So in some sense, you don't need to, you can insert everything. Then you can delete V. V here has the minimum 0. So this step also, it takes maybe V like V. So you are inserting every SP, guys. Then you will find the minimum vertex that the one has the minimum this. That was the heap structure. This is the delete min. And then you will do this operation. And now for every edge, if so for this is the heap that as we mentioned. So this is the vertex. So this is the vertex Z here. For every edge that we are considering, so we are considering this Z. For every edge that goes out of W, if the distance from, if the distance through W is less than the current estimate for Z, we will update Z. Now, when we update Z, we will consider here, this is the SP of Z here. So SP of Z is here. And then SP of Z for each edge that we update, it may only go down. It does not go up. So when it goes down, it means that in the heap, Now, if you consider its parent, so parent is another. By the way, we have also a link. So from each vertex Z, we have a pointer to where is it in the heap. So we also keep this data structure. We have an array that says what is the index or what is the place of this SP of Z. Now, we will go there, we will update SP of Z. SP of Z, I don't know, it might be, it is maybe 10. Now it becomes 8, a smaller number. It means that now if its parent was 9, before it was 10, it was less than its parent. But now it is 8 and less than its parents. So this is exactly the way that we were doing for insertion. We will insert, if you remember, we insert an element at the end of the heap. And if it's less than its parent, then we will just bring it up in the, so from the bottom, we are bringing it up. So here, exactly the same thing. SP of C may go down. So it means that the value of this guy, it might be less than his parents. So in that case, we need to do the exchange. So in this case, we are doing the exchange of these guys. So this guy becomes now 8, and this guy becomes 9. And again, we are continuing that one with his parents. If it's the other one, if the other guy is 7, then we are stopping. Otherwise, we may continue that. Good. And so this update for each edge, so this we are doing for each edge. For each edge, we need to do, so while we are doing that, we are updating the heap. And this one, essentially, as I discussed, this is like very similar to insertion. And so that would be order like V. So we will update it. We will find the next vertex, and any vertex that now we are finding the shortest path, the SP is minimal, we will delete it from the heap and we will add it to VK. And again, so I think, as I mentioned, so just summarizing it, we are running this line V times, and each time we are finding the delete mean. So it would be V times like V. And here for each edge, we are updating, and this updating the heap takes log V. So here would be size of E times log V. So the total things would be so yeah, so this one essentially the one that we are talking. So we are doing just the update would be just the insert, and then for each E we are doing it log V times. So it would be size of E times log V. And then this is the delete mean. The delete mean also for we are doing log V takes the mean delete or delete mean, and then there are V of them, V like V. So this plus this would be this final. And that's, as I mentioned, for DAGs, we could do a slightly better. There was no log V or log size of V. Yes. So this, okay. Any question?
Yeah. So when do we update S of W? If we're when do we
S of W will be updated when the edges incoming to W will be considered. So, so here in the algorithm, you see, here we are, in some sense, we are only updating SP of Z, correct? But this Z, I mean, this is just a name. If you consider W itself, it has also some incoming guys. So when, I don't know, you may call them W prime. So for those W prime, when we add W prime to V of K, then we will update also SP of W. Good. So always when the edges that are coming, in some sense, the SP of a vertex will be updated whenever We are considering incoming edges to this vertex. Good?
Yeah, so then that means like there isn't any destination like vertex. So like it's just finding the shortest path from the to all of the vertices.
Exactly. Yeah. This is exactly the thing that I mentioned. This is so this is the only difference that I mentioned. So we had all pair shortest path, that between any pair of vertices we find the shortest path. Here, this was the single source version. So the single source one is the one that you are finding the path, the shortest path from a given vertex V, which is a source, to everything else, to all other vertices. There is no particular thing. So you will compute this one for all vertices. Then if you want to find a shortest path from one vertex to another one, then you will just go and see that particular V. So you need to compute the whole thing. So there is nothing just to find the shortest path between S and a particular vertex W. You really need to find the vertex from V to everything else. And then you will go and see what is SP of W. Good.
Okay, yeah, that makes sense.
Great. Yeah. So for a few other note, I wanted to say that. So like whenever here, this is actually very similar to whenever the shortest path from a vertex. So we know that when we are adding this VK, when we have this VK, then we had another vertex Z that we are adding it to here. So this vertex Z is coming from W. So the shortest path comes to Z comes from W. In that case, actually you can create a tree as well. So whenever we will come for the first time to a vertex, so in this case, W would be the parent of Z. This is very similar to BFS. In the BFS, we have done exactly BFS tree. It was like that. That whenever you come from one vertex to another guy, that vertex would be the parent of this guy. So here, we know that the shortest path to Z comes from one vertex W, which was in VK. And that W becomes the parent of Z. And this tree, it is called shortest path tree. Good. That's one thing. The other thing is that if you want, so this guy is only gives you the estimate for the shortest path. What about if you want to find the shortest path itself? It's very similar to those dynamic programming things that we have mentioned. You can always, actually, this would be exactly the same thing. So whenever we are updating this one, SP of Z, you need to have essentially, like I will call it the path itself. Then in this case, we are putting the path of Z is equal to W. Actually, this path you can also call it parent of Z. So here it means that so the path through W is shorter for this. So in that case, the parent of Z in this shortest path tree would be W. Now, how can we find the shortest path? Again, exactly similar to those things that we have done it for dynamic programming. You will go to one vertex Z. You see who is this parents, W. Then who is its parents? Who is the parent of W? Then W prime, and so on and so forth, until you will reach V. This gives you the actual shortest path to yours. So whenever you want to find the shortest path, go to this Z, find who is the parent of Z that we have saved it already. Then who is the parent of this parent, parent of this parent, and so on and so forth, until you will reach V. That gives you the actual shortest path. This was the same thing also for all pair shortest path. As I mentioned, this is for all kinds of, this is also you can consider it as some kind of dynamic programming as well. So all of this, when we are updating, just keep the best person that, like the last person that updated this guy. From that, you can find essentially the path through the whole graph. And last but not least, we discussed this algorithm. This algorithm is like one of the early algorithms for shortest path, but it is interesting. Now, when you are using the Google Maps, for example, the way that they are finding the shortest path is actually the Dijkstra algorithm. I mean, they are just changing something for the like for example, intersection, etc., they may need to add some timing for them, because you consider the path that the time that you will go from intersection A to intersection B, but you may need to also spend some time in the intersection itself. But all of them, you can model it in a directed graph. And the actual algorithm that is currently in use in your cell phones, whenever you are going from one place to another one, and you are using Google Maps, actually you are using Dijkstra algorithm. So Dijkstra algorithm is at work at any time for you. So this is the algorithm that you should, remember that, like, whenever you take the path, I'm using that Dijkstra algorithm. And that is very exciting to know what is the inside of this algorithm, how this algorithm works. And the main algorithm is Dijkstra. There are, of course, some other details may be added to that, but the main core is Dijkstra algorithm for the Google Maps that finds the shortest path for. So it is very exciting actually to know about this algorithm and the details of that. Good, let me stop. Okay, so we are finishing this, and see you next time. Bye.